Okay, now I have here Baba Schwanson, who comes to tell you something called the gas scheme diagram, all right? So let's understand what the topic is exactly here. The topic, as we saw in the video that I showed you yesterday, and we saw, I even sent you the link for it. So we agreed that we have the JS, which I told you is a set of compartments, like a cabin, and it comes to the place where you are and starts to assemble together. So these compartments, regardless of whether they come as one piece or more than one piece, what is their purpose? The purpose is, first of all, like the idea when you have a big problem, you divide it into smaller problems to solve it or make it easier for you to repair. Similarly, you have your very large bay, which consists of two parts. One part has the bus bar, and there are parts in it, and the part that has or is the brake, or there's a city part, a T part. The part that has the cable or the part related to pushing that goes, for example, to the transformer or exits to the GIP, gas insulated passport, to go, for instance, to the gantry and then to the overhead transmission line or any of the things I'm talking to you about. The idea here is that I want to divide my GIP into a set of compartments. So what do I do? As you can see here, from this point to this point and then down to this part, these are compartments. So engineer, let me draw it for you here. This entire section, engineers, is like this, all of it. All right, and it goes down like this and down like this to this point. This is a compartment. Okay, great. The other part is that you have, let's make it in another color. Here we go. All right, this entire section too, although this color isn't really visible, here it is, it's the same color. Okay, this section here. Engineers. This entire section here, you have it like this, all the way to this point. Then it goes down to here. These are compartments, all right, and so on. So what's the idea? The idea is that these compartments as a whole are assembled. So if, God forbid, you have a crack, you have a problem in this compartment, you have insulation free, or you can check this compartment and replace it with another compartment, all right, great. Now, let's look at something very important, the symbols I have here. What's the idea? The idea is that in this compartment, you have this part which is marked with a dark color like this, all right? And you have small parts drawn here, and you also have other things like this view here, exactly the same as this, but not in dark color, not in black color. What is this? What are these symbols? Well, let's take a look. The first thing regarding this symbol, it means insulation spacer. What does it mean? It means insulation spacer. What is an insulation spacer? It's exactly like what we showed in our video about our cell. So I showed it to you yesterday and told you, here it is. This part that you see in white, we call it an insulation spacer. What does insulation spacer mean? It means that if this is a compartment, then this is called a gas, tight spacer, meaning the SF6 gas is trapped inside this compartment, creating insulation between this compartment and that compartment. And this compartment and that compartment, meaning this compartment is considered isolated so that the gas inside it here is not connected to the gas in the next compartment, nor the previous compartment, nor the first compartment. Of course, guys, what does this mean? It means gas tight, a gas tight spacer. Okay, nice, okay. So here, through our drawing, you now know that this shape means a gas tight spacer. And the shape that looks like it but is not a dark color means an insulation spacer of the type gas through. What does gas through mean? It means the gas can pass through it normally and move from this compartment to that compartment. As for its purpose, what is its purpose? Quite simply, let me draw it by hand for better clarity. I'll do it this way. All right, okay. Look, what are you? The whole idea is that you have, if I take it like this, now you have, for example, here it is, all right? And here, for example, all right? And the blue face is on the other side. They are three. If I look at you like this, all right? I mean, looking here like this from this side, like this, the three of them are something like this. It takes a shape similar to a triangle like this. Okay, if I look at them from the side like this, you'll see two and not see three. Nice, okay? Here, this is the place we call a gas tight spacer.
What does gas tight spacer mean? It means this place is sealed like this, and therefore the SF6 gas, the compressed gas we're talking about, will be here. This is not connected to the gas in this area or the gas in this area. Therefore, this means that if there is a crack here in this compartment or this compartment, the leakage that occurs in the SF6 gas is not related to the entire gas system, but only related to this compartment alone. The increase or decrease in pressure is related to this compartment, not related to this one, nor to this one, nor to the one next to it, and so on. This is referred to as a gas-tight spacer. What does gas-tight spacer mean? This spacer is this part, and gas-tight means that the gas is contained, meaning the gas cannot move from here to here or from here to here. And the same applies to the other side. If I tell you that this is a gas-through spacer, it means that the gas can normally enter from here to here and from here to here. So this means gas-tight spacer, and for example, this means gas-through spacer. So this is what gas-tight spacer means, and this here means gas-through spacer. Is that clear, guys? Okay, let's not forget. Is there a question? It seems like Mike's mic is open by mistake. No problem. So this is a gas-tight spacer, and this is a gas-raw spacer. And what is this gas? Gas-raw spacer. Excellent. Great. So now what's the purpose of this spacer? Generally, the presence of a spacer, whether it's a gas type or gas row, the idea is if you look at it from the side, right? I mean, if you look at it from here in a circular shape like we saw in the video, right? Where's the idea? The idea is that the passport running through shouldn't be extended 10, 20, 30, 40 meters, all stretched out without supports, right or wrong. So between this compartment and that compartment, it needs to rest on something with support. If you're talking about a tight spacer device like this, what? And if you're talking about a through spacer device, it would be like this. For the tight spacer device, I'm talking about something I've seen with my own eyes. You have your three phases here, and the rest of the middle part is all made of something like epoxy. As an insulating material, this is all epoxy. So now it's as if it's resting on the epoxy, which is the red part around it. As for the gas-tight spacer, I definitely can't make this entire area out of insulating material and rest on it. So, of course, epoxy is a solid material, not an insulating material. I'm talking about an insulating material. No, this is something with thickness. It has thickness, of course, which is nice. It's like I'm quickly sketching it for you. It has thickness like this, all right? So regarding the gas, how is it structured from the inside? Of course, it can't be a solid block of what? Of epoxy, and you only have 3 places for the bus bar to enter? No. Here, the epoxy is just the outer part like this. Okay, now you have one phase, the second, and the third. How does this touch the support for them? Here's the idea. The idea is that you have epoxy here on top like this. Taking this shape and holding this phase, and here on the side as well, epoxy like this is holding this phase. And you have epoxy here as well holding this phase. So these 3 phases, one is hanging from above and the other 2 are held from the sides. The area between them becomes a space, allowing the gas to move between this compartment to that compartment. Of course, I was not allowed to take pictures in the factory, so I'm sketching for you what I saw. So follow along, engineers. This means gas through spacer, and this means gas tight spacer. The spacer itself acts as a support to hold the bus bar, which can be 5, 10, 15, and so on in length. Additionally, as I mentioned, part of it is gas tight to prevent gas from passing from here to there, and part of it is gas through, which allows gas to pass. So the idea here is that I divide my compartment and always install the gas tight spacer so that in case of increased pressure or decreased SF6 gas pressure inside any compartment, or if there's a crack, the gas doesn't escape from the entire section, only from this compartment. So I have a problem. The second reason we divided them into a group of compartments is so that if there's an issue in any compartment, you can focus your troubleshooting, repair, or maintenance on that specific compartment. If something happens in that compartment, you can replace it instead of having to replace the entire unit. Engineer Fahd, you probably joined after I answered your question about the initiator. Indeed, the initiator, Engineer Fahd, is present in the high, but not in the medium. except in some stations where I've seen it. So you're asking about gas leakage. God forbid, is there any specific protection? Hold on, don't rush, Halisa. We haven't gotten into the circuits yet. We will delve into them in detail and talk a lot about it. All of this is just to read you the drawing keys that help you understand what the drawings in front of you are. So, as we can see, gentlemen, I have my compartment here in this shape. This compartment extends from here to here, passing through to this part. This compartment includes a piece of the bus bar with the switch here, and I have here a piece of the bus bar with the switch here, the CT in one compartment, the breaker in another compartment, and the CT after it in another compartment, and the line disconnector with the earth switch, and the line earth switch in the compartment, and the VT in the current compartment. Then you have the section below, which is a cable sealing end. Exactly. All of this is nice as you exit. Okay, nice. From the circuits, sorry, before these circuits, from the section you see here, from these two shapes, you always find them side by side like this. And you have this shape from the two side by side. These two side by side, you will find one of them here is a ruptured disc, and the other is something called absorbent zero. Okay, what is the idea behind these two? In every compartment, you will find these two side by side. In every compartment, you find these two side by side. First, the absorbent zero, which is considered silica gel, and it is indeed silica gel. You find a piece sticking out a bit like a cap covering it. This contains silica gel inside to absorb any moisture that might be present inside the SF6 gas. Why? Because as I told you yesterday, this is known not just from the course or the drawing that SF6 gas decomposes at the moment of a short circuit. The hydrogen present in the water vapor molecules, which are part of the SF6 gas components, decomposes, but of course in very, very, very small amounts. If it combines with fluorine atoms, it forms something called hydrofluoride. I told you that hydrofluoride is a chemically corrosive material, meaning it is a material that eats away at parts like the insulators, especially the spacers, and it erodes the epoxy itself. So, of course, it destroys the insulators, which is what absorbent zero does. Now, the other form is called the ruptured disc. What is a ruptured disc? The ruptured disc is a part of the GIS body. The entire GIS body is made, for example, from steel or aluminum, depending on the current rating. We're not focusing on the construction details here, so I won't delve into that. The important thing is that your body is entirely made of steel, and then you come to a specific part of it. What do? You make a part from a completely different material, which we call the ruptured disc. The purpose of this ruptured disc is to manage the pressure of the SF6 gas inside, which has a specific pressure limit. The increase in this pressure is allowed up to a certain point. If the pressure exceeds a level greater than this limit, in this case, to prevent the GIS body itself from exploding or breaking, this point comes into play. This point is weaker than the body itself. For example, if the body can withstand a pressure of 10 bar or 20 bar, this part can withstand a pressure of, for example, 8 bar, or if the body itself can withstand 20, it can handle 15 or 16. So if the pressure reaches 15, the body can still withstand it. But this part is a weak point in the GIS body, so it is the one that fails, allowing the SF6 gas to escape outside. Thus, I have preserved my GIS body, and I can later come and replace my ruptured disc. All right, great. Now let's move on to the fact that each compartment, just like it has the ruptured disc and the absorbent, every compartment must have a gauge to measure the pressure. So if I told you that here I have, for example, compartment 1, 2, 3, 4, 5, 6, and so on, and I told you I have 10 compartments, how many gauges would I have? Can someone write that in the chat for me? Stay with me. I always open the chat to see if someone is asking or saying something. So how many gauges would I have if I have 10 compartments? All right, if you're going to tell me that you would have 10 gauges, I would say you're correct, but there's a modification to that. What is it? You would have 10 gauges plus 1, making it 11. Why? Because the circuit breaker compartment is the only one that will have 2 gauges. All compartments have 1 gauge except the circuit breaker, which has 2, and we will understand why when we get into our control circuits. And the gauges, as you can see, have a shape drawn on them that looks like a worm. One with a white circle and the other with a black circle. The idea here is that this is called a check valve. What does check valve mean? We've all heard it in college. Check valve means a non-return valve, meaning this valve opens in one direction and does not open in the opposite direction.
One of them is normally open and the other is normally closed. What does this mean, engineer? The normally open one is the one that has its nature. Its nature is like this. It's just its nature. But as a result of the drawing, it shows you that there is a gauge attached to it. So surely the gauge presses on this valve inside to allow the SF6 gas pressure to reach the gauge so it can read its pressure. However, this valve is closed. You use this next part when you want to fill your compartments. Gas, or to fill or evacuate gas or from inside your compartments. All right, okay. And then you have here this round one. And of course, this is, guys, what is now recently available with us in every system to work on or predict if you have what. Recently, it has become available with us in every GEES. It performs online monitoring on the partial discharge to do forecasting or predict if you have any partial discharge or your insulation, which means that your insulation is on the way to collapse and that you will have an insulation breakdown because an institution is broken. Okay? Okay, there's also a part. I saw in the factory carefully because I used to see it in the summer, but didn't believe it. I saw it in the factory carefully as well, and I'd like to tell you about it. It's the part that looks like this, a part of the compartment that has a kind of pattern on it, and there's another one here in the middle. What is this part? They say it's due to a design difference. And as a result, the factory might not produce the compartment with the exact millimeter measurements as you want. So they always make a part like this. A part of the compartment here is made from alloy or a slightly different alloy with the same strength as the original alloy or the same strength as the steel itself, but with added elements that make this steel elastic. And here, what I'm going to draw for you is actually present. All right, let's go back here to this color. There is a long bolt here, all right. The head of the bolt is here, and here is your nut, all right. So the idea here is that if you apply force to it, you find that it does what? It compresses with you, meaning it gets pressed with you or expands with you. The maximum it can expand is 10 centimeters, and the maximum it can compress is 10 centimeters, assuming that if you bought it, your compartment, and came to install it on site, and God forbid, the design on your site itself is smaller or larger. Your compartment is off by 1 millimeter, 2 millimeters, 5 millimeters, and so on. So you have a part that can compensate for the error in these distances or these measurements. All right, I think we've covered this part. Now it comes to the point where you ask, what is the normal pressure? Press the SF6 gas to what pressure? For the sake of the 115 kVA level, it can withstand it without causing insulation failure. So for the 115 kV level, all compartments have the SF6 gas pressure inside at 400 kilopascals. This is at 20 degrees Celsius. Of course, we know that 100 kilopascals means 1 bar. So this means 4 bars, except for the circuit breaker, where the pressure is 6 bars. Of course, the circuit breaker is the place that opens and closes on loads. So it is a place where extinguishing or sparking can occur. So sparks might form there. All right, great. Then it comes to tell you about the setting pressure. What does setting pressure mean? Every gauge engineers has a 3. Engineer Fad, who asked me, I haven't shown you the goal scheme yet, but here I'm explaining that every gauge, this gauge, is analog and it has pressure on it. So it moves with the indicator. This indicator can move up or down. If it goes up, it presses on a limit switch, and if it goes down, it presses on another limit switch. All right, so you have 3 limit switches. One is for when you have high pressure, so this limit switch closes, and 2 are for when the gas pressure drops to the first level or the second level. So low pressure 1 and low pressure 2. All right, so when the pressure increases, a limit switch closes. And when the pressure drops to the first level, a limit switch closes. And at the second level, another limit switch closes. How many is that? Very good. Now, regarding all the compartments we mentioned, they are 4 bar. So what is the overpressure or high pressure? It is 5 bar. So Dr. Wilson at 5 bar means high pressure. Now, when it drops to the first level, which is 3.7 bar. The next level is 3.5 bar. For the breaker, it is 6 bar. So its normal is 6 bar. High pressure is 8 bar. Low pressure 1 is 5.5 bar. And low pressure 2 is 5 bar. Okay. You published it as 5 what? 5 bar? Okay. high pressure. So for you, this is the alarm and you don't take any action with it. We will see later when we connect it to the annunciator, okay? The 5.5 bar also triggers an alarm and you take action with it. And the 5 bar is an alarm and you also take action with it. All right, but the 5.5 bar means that the pressure has dropped to the first level. So this means you need to either refill your gas or do something about it. As for the 5 bar, if it reaches that, it means you have an issue with the gas system. Every part of it is just a knife switch, whatever it is, it's just a part of the passport, a ground knife switch, whatever it is, it's just the terminals only. As for the circuit breaker, if you have low stage 1, you will find it blocks the closing of the circuit breaker, but allows tripping. However, low stage 2 blocks both tripping and closing, not allowing the breaker to close if it's open, or open if it's closed. And we will see this within our control circuits. Each gauge of these is written in a certain way. It is written as gauge followed by XX-X. Now the gauge, and next to it, we write the number of your compartment, or let me say, sorry, your bay number. For example, if I am working in bay number 12, you will find it as G12-. The number that follows is the compartment number. 1, 2, 3, 4, 5, 6, 7. The breaker rate, of course, tells you what? G12, which is for bay, is number 12. 0 is an identifier number because it is the breaker itself. Then 1 and 2. All right, great. And then 4, 5, 6, 7, 8, 9, 10, 11, and so on, depending on what? Depending on the compartment in the game,